Quantum computing, from beginner to advanced. What if I told you that there are problems so huge, so mind-bogglingly complex, that every supercomputer on Earth, working together, would take millions of years to even scratch the surface? Now, what if I told you a new kind of computer could knock them out in a few minutes? This isn't some science fiction fantasy. This is quantum computing, and the revolution isn't on its way. It's already here. And you're about to get the roadmap. Forget what you know about computers. Seriously, the device you're watching this on, no matter how fast it is, works with a simple idea. On or off. 1 or 0. A world of black and white. But we're about to step into a world with an infinite number of gray areas. A world that plays by the wonderfully weird rules of quantum mechanics. This video is your guide. We're going to cover the whole journey, from the strange concepts at the core of the quantum world, all the way to writing and running your very first quantum program. By the end, the buzzwords will make sense, the path forward will be clear, and you'll get the fundamentals of the next massive leap in technology. Section 1. The why. Getting a feel for quantum. To really get why we need quantum computers, you first have to understand the brick wall that our current computers are hitting. For decades, classical computers have fueled our progress, but they're all built on binary logic. Their bits are like light switches, either on or off, a 1 or a 0. It's a great system for most things we do, but it has one major weakness. It chews through information one step at a time. For certain types of problems, like figuring out the exact behavior of a new molecule for a life-saving drug or finding the absolute best route for a global shipping network, the number of possibilities to check just explodes. It gets so big that even our fastest supercomputers just can't keep up. This is where quantum computing completely flips the script. It uses a totally different playbook. Instead of bits, a quantum computer has qubits, thanks to a cool principle called superposition. A qubit isn't just a 0 or a 1. It can be a 0, a 1, or a mix of both at the same time. Think of it like this. A normal bit is a coin flat on a table, either heads or tails. A qubit is that same coin spinning in the air. It's a blend of both heads and tails, and only when you stop it, when you measure it, does it land on one definite answer. This power to hold multiple values at once lets quantum computers explore a huge number of possibilities all at the same time. But superposition is just one part of the magic. The other, even more famous idea is entanglement. Einstein famously called it spooky action at a distance. When you entangle two qubits, they become deeply connected. No matter how far apart they are, across the hall or across the galaxy, their fates are linked. If you measure the state of one, you instantly know the state of the other. It's this strange, powerful connection that lets information be processed in ways that are just plain impossible in our classical world. It's superposition and entanglement working together that give quantum computers their world-changing potential. Section 2. The how. The pieces of a quantum program. So we've got these spooky, powerful ideas, but how do we actually use them to make something happen? That brings us to the nuts and bolts of quantum programming, gates and circuits. If qubits are the nouns of the quantum language, then quantum gates are the verbs. They're the actions that change the state of the qubits. Just like a classical computer has logic gates, like and, or, and not, to flip bits, a quantum computer uses quantum gates to manipulate its qubits. For example, there's a poly-X gate, which is basically a quantum NOT gate. It flips a qubit from 0 to 1 and back again. But then you get to gates that have no classical twin, like the Hadamard gate. This is one of the most important gates in quantum computing. It's the gate that takes a qubit sitting at 0 or 1 and pushes it into a perfect 50-50 superposition. It's literally the gate that spins the coin. When you put a sequence of these gates together, you get a quantum circuit. This is the quantum version of an algorithm. You set up your qubits. You apply a series of gates to put them in superposition and entangle them in very specific ways. And then at the end, you measure them. That measurement is key. It forces the qubits to fall out of their quantum weirdness and pick a side. a classical 0 or a 1. The whole art of quantum programming is designing a circuit so that when everything collapses, the chance of it collapsing into the right answer is as high as it can be. And holding all of this together is math. Specifically, linear algebra, the math of vectors and matrices, is the language used to describe qubit states and quantum gates. You don't need a PhD in math to start, but knowing that these circuits are really just pictures of elegant math is the key to going deeper. Section 3. The what? Let's write some quantum code. This all might sound wildly abstract, but here's the best part. You can do this right now, on your own computer. You don't need a super-cooled lab in your garage. Thanks to cloud platforms from companies like IBM, Google, and Microsoft, anyone can write quantum code and run it on powerful simulators and even on real quantum hardware. We're going to walk through what a Hello World program looks like using Qiskit, a popular open-source toolkit that uses the Python programming language. The goal of our first program is super simple. Create a state of perfect randomness to prove we've successfully used superposition. Here's the plan. First, you import the tools you need from the Qiskit library. Then you build a simple quantum circuit. We'll give it 1 qubit to work on and 1 classical bit to hold the final answer. Next, we do the magic trick. We apply that Hadamard gate we talked about to our qubit. This is the step that takes our qubit from a boring 0 state into that 50-50 superposition of 0 and 1. After that, we have to get our answer. We add a measure operation to the circuit. This tells the computer to look at the qubit, forcing it to collapse to either a 0 or a 1. That result then gets saved in our classical bit. Finally, we run the program. We tell Qiskit to run our circuit thousands of times on a quantum simulator. And what do we see? We find that about 50% of the time the qubit collapsed to 0, and 50% of the time it collapsed to 1. And just like that, you've written a program that directly uses the probabilistic nature of reality. You've taken your first real step on the road to becoming a quantum developer. Section 4. The what's next? The road ahead. That Hello World circuit is just the first step on a much longer and more amazing path. The real power of quantum computing comes from more advanced algorithms that are designed to solve very specific, very hard problems. For example, you've probably heard of Shor's algorithm. Its discovery in 1994 sent a shockwave through the world of cryptography because it can find the prime factors of huge numbers way faster than any classical computer ever could. Since most of our modern digital security relies on the fact that this is a hard problem, a big enough quantum computer could make our current encryption useless. This is exactly why there's a huge effort to develop post-quantum cryptography. Then you have Grover's algorithm, which gives a big speed up for searching through messy, unsorted data. A classical computer might have to check every single item in a database one by one. Grover's algorithm can find what it's looking for much faster, making it a powerful tool for all sorts of search and optimization problems. Of course, this advanced path has its own huge challenges. The biggest one is called decoherence. Qubits are incredibly fragile. The tiniest little vibration or change in temperature can make them lose their quantum state and crash the whole computation. This is why quantum computers are kept in extremely controlled, super cold environments. And it's why quantum error correction is one of the hottest areas of research. As scientists and engineers tackle these challenges, a whole new world of jobs is opening up. We're seeing a massive need for quantum algorithm developers, quantum software engineers, and quantum research scientists. These are the people building the hardware and software that will power the next generation of tech in everything from medicine and materials to finance and AI. We've covered a lot of ground pretty quickly. We started with the wild ideas of superposition and entanglement. We turned those ideas into the practical tools of qubits and gates. We saw how to put those together into a circuit to write a real quantum program. And we've looked down the road at the advanced algorithms and amazing career opportunities that are waiting. We are right at the dawn of the quantum age. Learning this stuff now is like learning to code for computers in the 1970s or for the internet in the early 90s. The potential is enormous. The field is moving at an incredible speed, and it's never been easier to get started. The journey from beginner to advanced is tough, but the path is clear, and it's a journey that could put you right at the front of a technological revolution. If you're ready to take the next step and really get into the powerful algorithms we mentioned, like Shor's and Grover's, make sure to check out our playlist on quantum algorithms right here. This path is a long one, and we're going to be exploring every corner of it. To continue your journey and get more deep dives into the quantum world, make sure to subscribe and ring that notification bell. You won't want to miss what's coming.